So, how do you solve a problem that feels, well, impossible? Sometimes the answer isn't some single flash of brilliance. It's a certain way of thinking. Today, we're going to dive into the engineer's mindset, this really systematic way of turning what look like catastrophic challenges into puzzles that can actually be solved. And we're going to do it all through a story set on the final frontier. And that idea right there, that conversation with the physical world, is really at the heart of our story. See, engineering isn't just about building stuff. It's a dialogue. It's a back and forth. You try a solution, the universe responds with data, and then you tweak your understanding based on that feedback. It's this constant unfolding process of discovery. All right, so our story starts right here on Station Harmony, which is this absolute marvel of engineering floating about 300 kilometers above the Earth. Think of it as a self-sustaining world in orbit. And our guide through all this is its lead engineer, Dr. Sarah Kovač. She's the one who's having that constant conversation with every single one of the station's complex systems. Now, on Station Harmony, everything exists inside a totally closed loop. It's not like Earth, where there are buffers. Here, every resource, every single molecule of air and water gets recycled. What that means is that every little component is connected to everything else. And a tiny, tiny error in one spot can ripple out and have absolutely massive consequences. And that brings us to our first problem, a mysterious 8% drop in the wheat yield. Now, this isn't just a little farming issue. No, this is an existential threat. If this trend keeps up, the station is going to run out of food in 6 weeks. The clock is officially ticking. So, how do you even begin to solve that? Well, this is where the engineer has to become a detective. The case of the failing wheat, as we'll call it, isn't about some obvious broken part. It's a hidden problem, and it's going to take a really systematic investigation to get to the bottom of it. And here's the real mystery. Every single one of the obvious variables, the soil, the light, the air composition, the temperature, all the readouts say everything is perfectly normal. The system is telling them, hey, we're fine. But the wheat itself is telling a completely different story. This is exactly the kind of problem where you have to look way beyond the surface. So this is where Kovač starts that conversation with the physical world. She doesn't just glance at the main numbers. She hunts for subtle patterns. And she finds one, a tiny 2% wobble in the CO2 levels. That little clue leads her to a hypothesis about bacteria in the soil, which then leads her to check the soil's pH levels. And finally, and this is the absolute key, she starts to question the tools themselves. What if the sensors, the very things telling her everything's okay, are wrong? What's happening here is a perfect example of a really important engineering concept, cascading failure. You can think of it like the ultimate domino effect. A tiny, almost unnoticeable error kicks off this whole chain reaction. The small CO2 imbalance feeds some bacteria, which then changes the soil's acidity, which then stresses out the plants, and that, finally, tanks the wheat yield. One tiny domino falls, and the whole system starts to wobble. And there it is, the first domino. A single carbon dioxide sensor was off by just over 0.5%. That tiny, tiny error, compounded over weeks and weeks inside this closed system, was enough to threaten the entire station. And that's the core lesson, right? In really complex systems, the smallest details matter more than you can possibly imagine. Okay, so with that immediate crisis solved, Kovač has to face an even bigger challenge, doubling the station's size. Now, the whole mindset has to shift from just reacting to problems to proactively designing a system that expects things to go wrong. You have to plan for failure. And this is the fundamental challenge when you try to scale anything up. A visiting expert, a Dr. Wei, just nails it with this quote. When you double the number of parts, you don't just double the risk. The number of ways things can break absolutely explodes. Because it's not just the parts that can fail anymore, it's all the new connections between them. Failures really come in two main flavors. On one hand, you've got your simple component failures. A pump breaks, you just swap it out. You can predict that. But on the other hand, you have interaction failures. And this is when two perfectly working parts somehow clash in unexpected ways, like a new software update that just doesn't get along with the old hardware. These are the real hidden dangers in any complex system. So how do you even design for that kind of chaos? Well, you use these 4 principles. Isolation basically contains the damage. It's like a firewall. Redundancy means you got automatic backups ready to go. Intelligence means the system itself is smart enough to spot and diagnose its own problems. And transparency, this one's so important. It means a human can actually look at the system, understand what's happening, and step in to fix it.
And it's a good thing they had those principles because they're about to get a serious real-world test. We're about to see a live crisis, a cascading failure happening in real time, where every single second is going to count.
Suddenly, an alarm goes off. Oxygen levels in one of the agricultural cylinders are spiking, and I mean spiking fast. This isn't a long-term problem like the wheat yield. No, this is an immediate, deadly fire hazard. The whole station is now at risk. Now, just look at how this all unfolds. Right at hour zero, the system's intelligence spots the problem instantly. But a couple hours in, the automation can't keep up. So this is where that human transparency kicks in. The crew understands the system so well that they can intervene manually, buying themselves precious time to find the root cause, which turns out to be a single failed regulator, and then fix it. It's this perfect partnership between the human and the machine. So here's the really crucial takeaway. The crisis wasn't just stopped. It became a lesson. That failed part revealed a hidden weakness. They were pushing these components way past their designed limits. So this failure wasn't just a problem to be fixed. It was priceless data that made the entire station stronger and way more robust for the future. And this really brings us to the legacy of this whole mindset. Each of these solved problems, the failing wheat, the resilient expansion, the oxygen crisis, they aren't just one-off victories. They actually become the foundation for everything that comes next. This is the real engine of progress. It's called cumulative knowledge. Civilization doesn't just leap forward because of some sudden flash of genius. It advances bit by bit, with each generation building on the lessons learned and the mistakes made by the last one. Every problem you solve is another brick in the foundation. And you can literally see this process playing out over decades. The lessons they learned from Station Harmony are what directly made it possible to build a station around Mars 20 years later. And the knowledge they gained from that project is what makes a deep space mission even thinkable. Progress isn't a straight line. It's a series of building blocks, each one built on the successes and, the failures of the one that came before. Which kind of leaves us with this final thought. This engineering mindset, it's not just for space stations. It's a way of looking at any complex challenge, in climate, in medicine, even in our own lives. It's a powerful reminder that the biggest, most impossible problems we face are often just a series of smaller, solvable ones, just waiting for a patient, systematic conversation with the world.